We are now in the era of Vera Rubin, where we are receiving an enormous amount of information from this incredible observatory that is taking new images every few seconds and sending data back to the US, which is then being put out into the hands of data brokers, and astronomers can look over and see discoveries of new supernova within a couple of minutes. Like, the logistics of this boggle the imagination. And yet right now you can go to one of 7 data brokers, browse their websites for new supernova and new various events, or you can actually write your own custom Python code and use their APIs to filter it down for exactly the kind of information that you're looking for. If you want to discover supernova, you want to discover asteroids, you want to discover comets, this is the way you'll do it. So my guest today is Dr. Tom Matheson. He is the head of time domain services at Noir Lab, and they are running the Antares data brokerage for Vera Rubin data, as well as a lot of other telescopes as well. And so I want to just get a sense of what it's like to run one of these, to watch the data streaming by, and to also give people information about how they can actually plug into this and develop their own apps. We live in this amazing time where you can use an AI assistant like Claude Code to help you develop an API that will let you connect into this and filter this information for whatever you want. Make your own discoveries. This is the time. So if you want to learn more about this, check out this interview with Tom Matheson. Tom, you have been sort of preparing for this moment for years, and now here we are. The flood has arrived of data from Rubin. What's it like watching over this?
Well, I mean, it's been really exciting. And, also there's that little relief in the back of your head, because even though we've done testing and we've been doing live alerts from the Zwicky Transient facility for years, until you actually do the real thing with real Rubin alerts, you don't know that it's going to work. And to see that actually happen in real time was really fantastic. Although, I mean, to do a real test, you want it to be automatic. So for the second night when we were testing, my developers and I actually stayed away just to make sure it would work without us there.
Oh, right. Of course. Yeah, I've been through this as well, like where you develop like a series of automated things that are all supposed to trigger based on stuff. And then, one part of the pipeline receives a bad piece of information and just locks up and doesn't do what it's supposed to do. And you're just like, why aren't you moving?
Right.
And so, yeah, to walk away and just go like, I'm sure the system's going to work, has got to be unnerving, but also quite satisfying when you come back and it did its job.
Oh yeah, and it was a great feeling to see that everything worked, and not just our systems, but like across the whole follow-up system that we put together in the Noir Lab. Everything worked great. It was really fun and just a rewarding night, because we've been waiting for a long time for this.
Yeah. So, give people just a sense of what the chain of events that's happening to make these data available to astronomers to be able to review within minutes, really, of when the images are being captured.
Yeah. So, I mean, the Rubin camera has a huge field of view, as you know. And so every time they take an image, they will take a template of that they have of a previous image of the same place on the sky and digitally subtract that image. And they'll be able to see anything that has changed, and that is changed in brightness or in position. So moving objects also get picked up by this. And so that process is automatic. The data are taken in Chile. They flow up to the US data facility at SLAC at Stanford, and the processing happens there. The image subtraction is handled there. And anything that stands out as new gets sent out in an alert stream. And so this has each alert, each event has its own little packet of information that flows out. And these go out from that data center to the various data brokers that Rubin has selected around the world. And there are 7 of them that are doing the full scale of this, and each of them gets this full stream of alerts. And then from within those brokers, that information is accessible to astronomers in lots of different ways. You can either go to their websites, there are ways that they stream out filtered alerts. So there's a whole wide variety of ways for people to interact with this. And not just professional astronomers. Anybody can go look at these websites and play around with the alerts and see what's there. So, we try to make this as accessible as possible for people to look and see what's happening with the Rubin alerts.
Yeah. So why was there this sort of decision made to go with data brokers as opposed to it just being sort of like just this raw API feed that programmers could plug into and work from?
Well, I mean, I think the original decision was that trying to find a way to process the alerts was just too big of an addition to the Rubin construction project itself. I mean, the data management system for Rubin is already a very complex and extensive system, and adding something else like this would just be yet another further complication. So they made a decision to constrain what they're doing in that project, right? So they would take the alerts up to that point, and then they would make them available to the community. The fact that there are brokers out there was something they counted on happening, that the users out there would build systems to accommodate that flow of alerts. And then the brokers are designed in a way to make it easier for astronomers and other people to interact with the data. If there was just this raw stream of millions of things coming every night, if every individual was trying to look at that would be really hard for them, right? I mean, you sitting at your computer, sorting through 7 million objects a night, I don't know how you're going to do that. But if you can rely on somebody else, like the system we built, to do some of that processing for you, then instead of seeing 7 million, you see like the 7 things that might be interesting to you. And then you can, that's something that a human can digest and go work on for the things that they want to follow up.
So, okay. So yeah, that makes a ton of sense, that essentially you've got the raw feed, everything that has been detected that night, the 800,000 events today, the 7 million events when they get fully up operational. And then that is gathered up by the various data brokers like the one that you're working with. And then that information is analyzed. So what kind of analysis are you doing on the data?
Well, I mean, there's a huge variety of things that you can do with the data once you have it in a system that can process it. And so our filters, that's what we call the things that sort through the alert stream to try to find objects of interest. They can be really simple, right? Some people with small telescopes might want only the brightest things, right? But they can't look at the faint things. So that's simple to do. Or it might be that there's a particular galaxy you're interested in and you want to know if something happens there. So you can put an aerial constraint and say, if there's an alert that happens here, then we definitely want to know about it. But we can also accommodate really complex filters. So things that are like machine learning based light curve classifiers. So if there's a model that someone has built to look at a light curve and say, oh, comparing that with everything we know from previous light curves, we can say that this is likely to be this kind of supernova or something like that. So we can deploy that kind of filter as well. And that's one of the advantages of the platform that we've designed, is that anybody can, if you have an algorithm and can write it into Python, we can deploy it on our system and find your objects for you. So it's really that we're not doing the analysis for you. We're providing you with a platform that lets you do it.
Right. So essentially categorizing and normalizing all the data so that I can say, I want to be alerted every single time there's a type 2 supernova.
Exactly.
In this galaxy or in this region of space or at this Z distance, at this redshift distance or whatever. And then you can have these kinds of triggers show up for you. And so how has the response been from the astronomers?
It's been really amazing. There's nothing like a deadline of the alerts suddenly becoming available for astronomers to start acting on it. So there's been a lot more interest in putting filters in, and we've had a lot of people developing things that they want to deploy on the system. So it's been really great to see this really sudden uptick in activity now that the alerts are live and people can really start to work on the things that are coming from Rubin. So that's been great to see the activity on that.
And what is the availability of this? Like, what kind of credentials do you need to have to be able to put in search filters?
So for our system, there are no requirements. If you have an idea and it'll work in our system, we're happy to deploy it. If you're going to do something that is so complex it brings down our system, we might need to talk to you about how to write it in a better way. But for the most part, we don't put any restrictions on anything. The Rubin alerts are world public. There's no proprietary restrictions on that, and we don't put any restrictions on the use of our system either. So you don't have to be a professional astronomer. If you've got an idea and you think that we can provide something to help you, we can do that.
Right. So if I want to, for example, be notified every time there's a object that has a magnitude of greater than 14, for example, something brighter than that, something that I could see in a small telescope and take a picture of, then I could set that up and be good to go in the system.
Oh yeah, and
Yeah.
that's an easy thing to do, and we actually do that with the Zwicky Transient Facility for a college in New York that has a smaller telescope because they can't look at the fainter things, so we send them the brighter things, and they're happy to get that. So this is a pretty straightforward thing to do that can help people sort of at all levels in terms of what access they want to do or what things they're interested in within the string.
And then I wonder how discovery and stuff is going to work. I mean, say an asteroid or the thousands of asteroids that were discovered last night. How do you, who has discovered it? Did Rubin discover it, or did you, as a person who identified it in the data and did the first announcement of it?
Right. Well, I mean, I should say, especially for the solar system things, that's a sort of a very special category, right? The unknown ones, that's an on-project thing. So Rubin tries to identify the new objects, and for the known solar system objects, that goes to a special solar system broker that's operated up at Northern Arizona University. So anyway, but for things that are discovered, whoever is the first to identify them really gets credited with the discovery or the naming rights, or however you want to think about it. And, for example, we've already had this with Rubin where people have followed things up and reported them to the transient name server. That's the official IAU clearinghouse for transient events. And so people are already, putting those things in and saying, hey, we discovered this and we were the first to show that this was, some type of supernovae or something like that. So, there's a lot of interest in being the first and finding these objects. I think the thing to remember, though, is that, this isn't a sprint. We've got 10 years with millions of alerts every night. So in the end, the numbers are going to be the important thing, right? The statistical analysis of many, many events. So discovery is important, but I also think we need to think about, it's also a 10-year project that we'll be able to mine the data for a long time.
Yeah, someone sent me a filter that they had run on just one night's data, and all of the objects that were brighter than, I think, 16th magnitude, the kind of thing you could see with, say, an 8-inch telescope with a good camera system. Mm-hmm. And it just went on forever, right? Like, what are you supposed to do with that, right? Like, one object could be a paper for a scientist they could spend almost their entire career working on a class of objects, and that's just the fire hose is just rolling past you night after night after night. I wonder if people are just going to burn out on the amount of data that's coming at them. And I think you're exactly right. Like, whoa, this is a marathon, not a sprint.
No, exactly. And I think that people will initially jump on sort of the interesting objects that might be, but I think there will come this realization that this is a machine that's going to collect a lot of data. And so it's what we do with that in the long run that will really provide some, interesting answers about things we don't yet know about the universe. And so I think that there are sort of two aspects to it, right? There's this real time, that interesting thing that might be so rare that there are hardly any of them. But then there's also all the other things that we kind of know about, but it would be great to have samples instead of the thousands we have now of millions. And then you could really start to break them into different categories and try to understand them at a level that has just been impossible up till now.
So have there been any things, I don't know if you've even had time to consider it as an astronomer as opposed to just trying to make the machine run, but has anything popped out so far just in working with it, or have you got any good stories yet?
On the very first night when we were testing, we were able to find supernovae immediately. I mean, the things that, in the old days, people would, spend nights searching through plates trying to find these, and now we can just find them, constantly in almost every image they take, there'll be a new one. So that was really interesting to see. In terms of trying to find something that is completely new, we haven't been able to get there yet. But that's the goal, right? The goal is, if we can eliminate all the things we know, then the thing that's left is the thing we don't know. And it'd be really interesting to find those, because Rubin will find that kind of stuff. Every time domain survey we've ever run has yielded things that we didn't know about. Things we didn't even predict, right? And so I'm sure that'll turn up in this survey as well. The hard part is you got to find it among all the rest of the things. But, it's a classic needle in the haystack problem, where you find the needle, in this case, by removing the hay. And so we identify everything we know, and what's left is hopefully something really interesting.
Yeah. That by observing so many objects, detecting, and then being able to filter out all the stuff that you all the boring stuff like type 2 supernova and type 1a supernova and
Well,
moving asteroids.
we don't say anything's boring because
No, I know.
it's exciting to
I'm
somebody
saying that
somewhere.
ironically. Yeah.
Yes.
Removing the boring,
Yeah.
transient tidal disruption events and the variable stars and all of that. Then hopefully you're left with a bunch of genuine mysteries, things that are behaving in ways that nobody's ever seen before. Each one of those then is an entirely new class of object to try to understand.
No, exactly. And I mean, that's been one of our goals all along is how do you find that unknown? Because, and there are machine learning techniques to try to find anomalies in these distributions of things. So, we're deploying things like that to try to identify stuff we've never seen before. But it's going to take a while to understand the system and the data that it's giving to us. So I'm not sure we're going to see that immediately. And it's going to take them a while to get templates across the sky and really observe in the way that we expect. But I'm certain that we will find stuff that we've never seen before. And it's going to be really exciting. I mean, that's the goal, right? With the time domain here is to find the things we haven't seen. Astronomy is still a discovery-based science. And, we're constantly surprised, which is great. I mean, that's the fun part, right?
Yeah. And so, my audience, I'm gonna sort of say that a big chunk of my audience are lapsed astronomers. They are people who love astronomy, but for whatever reason weren't able to go into that as a career, but in their heart, that's their true career passion. And now they're going to bring their programming expertise, their, sort of that knowledge to bear on what is now essentially the largest public archive of what's happening in the night sky, night after night after night. And so how would you recommend, I'm sort of imagining a person who their day job is they're working as a programmer at Google or Apple, and they are, they're very familiar with databases and APIs and Python, and they're doing all that, but they want to contribute, they want to participate, maybe they want to try and discover an asteroid or two. How should they sort of proceed?
Well, I mean, the direct access to all these alerts would be through the brokers. And so I think you can go and look at the various ones that are available. Antares is the one that we built here at Noir Lab. But the other ones, they're all good. I mean, people should look at them and they're all have their strengths and weaknesses, and people should go and look at each one and see if it does something akin to what they want to do. And there's a lot of variety there. For our system, we are pretty open. So if you come and look to our website and look at our instructions on how to write a filter, people could jump right in and start doing that really quickly.
Especially with these automated, like Claude Code and codecs and stuff. All of these modern AI tools are really good for this kind of thing.
Right. And we provide example code of filters that, so it's easily available to anyone who wants to see how it works. And the other thing is that all the information in the alert is available to you to work with the filter. And we provide all this contextual information. We cross-match every alert with other catalogs. So if you want to do something that's only in a certain type of galaxy, we already have that information available for you to work on in your filter. So across the multi-wavelength catalogs, all that history of astronomical information is attached to the alert through our system. And you can use that in your filter to try to find something that you want to look for. So we want to make sure that we have as much information available to people as possible, but we also want to make sure it's easy for people to come and use our system, because that's the goal, right? Is those, the full stream of millions of alerts is just impossible for any one person to do. And so we want to make sure that the science gets done without having to worry about all of that underlying infrastructure that we've put together. So we've hopefully done it in a way that makes it easy for people who want to do science. And that doesn't have to be a professional astronomer. It can be anybody who's got a good idea.
Is there a mystery that you would love to see explained?
Well, there are many mysteries that I've been interested in over the years. We'd really like to know what type 1a supernovae really are, in terms of what is the standard type 1a? What is the actual variation in their brightness mean, right? That would be very interesting to understand in and of itself, but it would also be tremendously valuable in cosmology because, of course,
Yeah.
that's how we do distances to very, high redshift galaxies. And so that's how we discover dark energy. That's how the Hubble tension is known. If we understood that better, we might actually be able to see more precisely what the expansion history of the universe is. So that's one thing, but I think the thing that really excites me most, like I said, is to find the stuff that no one even expects, right?
Right. The things I always describe as the things the universe was doing when we weren't looking.
Right. Exactly.
Yeah. Now we're looking.
These things are happening, right? But we've never been able to catch them just because the surveys haven't been extensive enough. And now we have a survey that essentially catches everything. And so that'll be great. It'll find, that 1 in a billion thing, the 1 in a billion thing will happen frequently in their data stream.
So if people want to search for this, it's Antares at Noir Lab, and that will get to them.
Yeah, that'll bring them to our website. And, you can go there and you can look at Rubin alerts right now. We have, we've ingested all the historical stuff. I mean, we did like 10 million over the last 3 days. So,
yeah, again, the scale. It's funny, like, you mentioned Type 1a supernova, and up until this point, astronomers have painstakingly built up a collection of about, say, 3,000 Type 1a supernova. Right. And Rubin's going to give us 1 million.
Yeah.
At least.
Oh, yeah. And, no, it completely changes the dynamic, especially because then you can choose subsets that are very well defined. And you might be able to understand, is it the host galaxy that influences the differences we've seen or something else? And that'll be really interesting to know.
Yeah. Yeah. Wonderful. Well, Tom, congratulations on sort of, I guess, handling the fire hose so far. And I really look forward to the discoveries that are going to be made shortly.
I mean, I should say that one of the great things about this is I've had a fantastic team of software developers who've built this, and the real hard work they did. So they deserve all the credit for how well things have worked.
Well, then I take it all back. Congratulations to the team for putting together, handling this. And now it should just be smooth sailing from this point on.
Sure. Nothing can go wrong.
Yeah, exactly. All right. Well, thank you so much.
Sure. No, happy to do it.
I hope you enjoyed this conversation with Tom. I'm going to give you some final thoughts, but first, I'd like to thank our patrons. Thanks to Abe Kingston, Andrea Pedretti, Bear League Roofing, Brian Bodie, Caradwin, Chuck Hawkins, Commander Baylor, Cooper and Ellie, Dark Finga, David Gilton and David Matz, Evan.Pro, Greg Feely, James Clark, Jeremy Mattern, Jim Burke, Jordan Young, Josh Schultz, Marcel Smith, Michael Purcell, Nordspace, OneSetForAnimals.org, Paulbach, Brankaidu, Richard Williams, Sean Sargent, Stephen Fowler Munley, Team 49, Telescopes Canada, Wolfgang Klotz, and Zeldabor Galactic Defender, who support us at the Master of the Universe level. And all our patrons, all your support means universe to us. So I'm really excited about this, and I feel like this is a moment where this data are very, very accessible to anybody who really wants it. And if you are one of those people that I mentioned in the interview, if you are a lapsed astronomer, if you are if you wish you could have been an astronomer, this is your chance that you can very easily, if you have the programming skills or if you understand how to use one of these AI tools, you can develop a code base that will let you connect in and start filtering the data for things that you want or things that you're interested in. You want to be alerted every time there's a supernova that could be bright enough to see with the unaided eye, you could do that. If you want to know the moment they find Planet 9, you could probably do that too. That might be tricky, but anyway. And so this is the moment. And that people are going to make discoveries. People are going to be able to assist and help categorize, do citizen science on all of these data that are coming down from Vera Rubin. So hopefully this gets you enthusiastic about it. This is going to give you another project to work on, but I think it'll be worth it. All right, we'll see you next time.